Chapter 7, Logical Mathematical Intelligence. Piaget was fond of relating an anecdote about a child who grew up to be an accomplished mathematician. One day, the future mathematician confronted a set of objects lying before him and decided to count them. He determined that there were 10 objects. He then pointed to each of the objects, but in a different order, and found that, lo and behold, there were again 10. The child repeated this procedure several times with growing excitement as he came to understand, once and for all, that the number 10 was far from an arbitrary outcome of this repetitive exercise. The number referred to the aggregate of elements, no matter how they happened to be acknowledged in the sequence, just so long as each of them was taken into account once and once only. Through this playful dubbing of a group of objects, the youngster had, as all of us have at one time or another, arrived at a fundamental insight about the realm of number. In contrast to linguistic and musical capacities, the competence that I am terming logical mathematical intelligence does not have its origins in the auditory oral sphere. Instead, this form of thought can be traced to a confrontation with the world of objects. For it is in confronting objects, in ordering and reordering them, and in assessing their quantity, that the young child gains his or her initial and most fundamental knowledge about the logical mathematical realm. From this preliminary point, logical mathematical intelligence rapidly becomes remote from the world of material objects. By a sequence to be described in this chapter, the individual becomes more able to appreciate the actions that one can perform upon objects, the relations that obtain among those actions, the statements, or propositions, that one can make about actual or potential actions, and the relationships among those statements. Over the course of development, one proceeds from objects to statements, from actions to the relations among actions, from the realm of the sensory motor to the realm of pure abstraction, ultimately to the heights of logic and science. The chain is long and complex, but it need not be mysterious. The roots of the highest regions of logical, mathematical, and scientific thought can be found in the simple actions of young children upon the physical objects in their worlds. In describing the early development of language abilities, I found myself drawing on the works of numerous scholars. When it comes to the ontogenesis and development of logical mathematical thought, one scholar's work is preeminent. Accordingly, in what follows, I build upon the path-breaking research of the Swiss developmental psychologist Jean Piaget. In Piaget's view, all knowledge, and in particular, the logical mathematical understanding that constituted his primary focus, derives in the first instance from one's actions upon the world. Accordingly, the study of thought should, indeed must, begin in the nursery. Here one beholds the infant exploring every manner of objects, nipples, rattles, mobiles, and cups, and soon enough coming to form expectations about how these objects will behave under diverse circumstances. For many months, the child's knowledge of these objects and of the simple causal connections that exist among them is tied completely to his moment-to-moment experience with them. And so, when they disappear from sight, they no longer occupy his consciousness. Only after the first 18 months of life does the child come fully to appreciate that objects will continue to exist even when they have been removed from his time and space frame. This attainment of a sense of object permanence, that objects have an existence apart from one's particular actions upon them at a given moment, proves to be a crucial cornerstone for later mental development. Once the child appreciates the permanence of objects, he can think of and refer to them even in their absence. He also becomes able to appreciate the similarities among certain objects. For instance, the fact that all cups, despite differences in size and color, belong to the same class. In fact, within a matter of months, the child becomes able to effect groupings on this basis. He can put together all the trucks, all the yellow cars, all the baby's toys, though as a young toddler he does this only fitfully and only if he is in a cooperative mood. The ability to group together objects serves as a public manifestation of the child's emerging knowledge that certain objects possess specifiable properties in common. It signals, if you like, the recognition of a class or set. However, for a few years, such a recognition lacks a quantitative aspect. The child is aware that there are larger and smaller piles, more or fewer coins or M&Ms, but these understandings remain at best approximate. True enough, the child may have a mastery of very small quantities, 2 and 3 objects that he, like some birds and certain primates, can recognize by simple inspection. But he lacks the crucial understanding that there exists a regular number system, with each number signifying one more, plus 1, than the previous one, and that any set of objects has a single, unambiguous quantity. This failure to conserve number is borne out by the fragility of counts in the face of competing cues. For instance, the child who beholds two arrays of M&Ms, one covering a wider space than the other, is likely to conclude that the more widely dispersed pile contains more candies, even if in fact the other, denser heap is the more numerous. Except for very small amounts, sheer quantitative estimates are still overwhelmed by perceptually seductive cues, such as density or spatial extension. Often at this age, the child can count. That is, he can recite the rote number series. But until the age of 4 or 5, this rote performance, essentially a manifestation of linguistic intelligence, remains removed from his simple estimates of small sets of objects and from his ability to assess the numerosity of a larger array. But then pivotal events ensue. The child learns that the number series can be mapped onto arrays of objects. If he says a single number after pointing to a single object, and repeats this process with each succeeding numerlog in the series, he can make an accurate assessment of the number of objects in an array. The first object touched is number 1, the second is number 2, the third is number 3, and so forth. The child of 4 or 5 has come to realize that the final number in this oral recitation is also the totality, the cardinal quantity of objects in an array. Finally, by the age of 6 or 7, the child has reached the level of Piaget's young mathematician to be. Confronted by two arrays, the child can count the number of entities, M&Ms or balls, in each, compare the totals, and determine which, if either, contains the greater amount. No longer is he likely to err, for instance, by confusing spatial extent with quantity, or to reach a wrong total because he fails to coordinate his pointing with his numerical recitation. Indeed, he has arrived at a relatively foolproof method of assessing quantity, and has, at the same time, gained a reasonable grasp of what quantity means. The processes involved in mastering such equivalences play an important role in Piaget's view of intelligence. In equating two arrays on the basis of number, the child has in effect created two mental sets or mental images, two arrays. He is then capable of an action of comparison, contrasting the number in one set to the number in another, even if the sets are not identical in appearance, and even, for that matter, if they are not both available for inspection. Once such actions of comparing have been mastered, the child can undertake additional operations. He can add the same number of elements to both, and the result of these two adding operations will yield identical sums. He can subtract equal amounts and again confirm equivalence. More complex operations become possible. Beginning with non-equivalent amounts, he can add to each the same quantity, secure in the knowledge that non-equivalence will be preserved. On his own, or with help, the child can evolve the understandings needed for the gamut of basic numerical operations, adding, subtracting, multiplying, and dividing. And by the same token, he should be able to call upon these operations in negotiating the tasks of daily life, buying goods at the store, trading with friends, following cooking recipes, playing marbles, balls, cards, or computer games. The actions just described may be, and at first generally are, performed physically upon the material world. That is, the child actually manipulates the candies or marbles as he is engaged in numerical operations. Similarly, other elementary forms of logical mathematical intelligence. For example, the child's initial appreciation of causal relations and his first efforts to classify objects consistently are also manifest at first through observation and manipulation of physical objects. In short, according to this analysis, the basis for all logical mathematical forms of intelligence inheres initially in the handling of objects. Such actions can, however, also be conducted mentally inside one's head. And after a time, the actions in fact become internalized. The child need not touch the objects himself. He can simply make the required comparisons, additions, or deletions in his head, and all the same, arrive at the correct answer. If I were to add two objects to the pile, I would have, he reasons to himself. Moreover, these mental operations become increasingly certain. No longer does the child merely suspect that two different orders of counting will yield 10 objects. He is now certain that they will. Logical necessity comes to attend these operations, as the child is now dealing with necessary truths, not merely with empirical discoveries. Deductions, tautologies, syllogisms, and the like are true, not just because they happen to confirm a state of affairs in the world, but also because certain rules of logic must apply. Two piles remain the same, not because a count reveals them to be identical, but rather because you haven't added or taken anything away, and therefore they must remain the same. Yet, for the period under discussion, roughly the ages of 7 to 10, these actions, whether physical or mental, remain restricted to physical objects, which at least potentially can be manipulated. Hence, Piaget terms them concrete operations. Further cognitive growth is essential before the child reaches the next, and for Piaget, the final stage of mental development. During the early years of adolescence, at least in the Western societies studied by Piagetians, the normal child becomes capable of formal mental operations. Now he can operate not only upon objects themselves, and not only upon mental images or models of these objects, but also upon words, symbols, or strings of symbols, like equations, that stand for objects and for actions upon objects. He is able to state a set of hypotheses and to infer the consequences of each. Where once his physical actions transformed objects, now mental operations transform sets of symbols. Where once the child added balls to each pile and confidently declared that the totals remained the same, now the child adds symbols to each side of an algebraic equation, secure in the knowledge that equivalence has been preserved. These symbol-manipulating capacities prove of the essence in higher branches of mathematics, with the symbols standing for objects, relations, functions, or other operations. The symbols to be manipulated may also be words, as in the case of syllogistic reasoning, scientific hypothesis formation, and other formal procedures. While the performing of operations upon equations will be familiar to anyone who recalls school mathematics, the use of logical reasoning in the verbal sphere needs to be distinguished from the rhetorical language that we encountered earlier. One can, of course, make logical inferences that are consistent with common sense. The same rules of reasoning can be equally well applied, however, to apparently unrelated statements. Thus, given the assertion, "If it is winter, my name is Frederick," and the fact it is winter, one can infer that one's name is indeed Frederick. But the procedure does not work in reverse. Knowledge that one's name is Frederick in no way justifies the inference that it is winter. That inference would be valid only if one had been given the assertion, "If my name is Frederick, it is winter." Such sets of phrases, which delight logicians almost as much as they infuriate the rest of us, serve as a reminder that operations of logic can be, and routinely are, carried out quite apart from common sense applications of ordinary language. Indeed, only when the statements are treated like elements or objects to be manipulated, rather than as meaningful utterances to be pondered, will the correct inferences be drawn. Note that in these cases, the kinds of operation carried out earlier with objects themselves have now resurfaced with reference to symbols, numbers, or words that can substitute for the objects and events encountered in real life. Even a 3-year-old can appreciate that if you pull lever A, event B will follow, but the parallel inference on the purely symbolic plane takes several years to evolve. Such second-level and higher-level operations become possible only during adolescence, and if luck and brain cells hold out, afterward as well. And they may sometimes attain such complexity that even otherwise highly competent individuals cannot follow all the processes of reasoning in the chain. The sequence of development outlined here, Piaget's account of the passage from sensory-motor actions to concrete to formal operations, is the best worked-out trajectory of growth in all of developmental psychology. While many parts of it are susceptible to criticism, it remains the account of development against which all other formulations continue to be judged. I have traced its path with regard to a single topic, the understanding of number and of number-related operations, but to suggest that the sequence is limited to numerical understanding would be a gross error. Indeed, the state of affairs is precisely the opposite. According to Piaget, this developmental sequence obtains in all domains of development, including those Kantian categories of special interest to him: time, space, and causality. Piaget's fundamental stages of development are like giant cognitive waves, which spontaneously spread their principal ways of knowing across all important domains of cognition. For Piaget, logical mathematical thought is the glue that holds together all cognition. My major bone of contention with Piaget has already been revealed in earlier chapters. In my view, Piaget has painted a brilliant portrait of development in one domain, that of logical mathematical thought, but has erroneously assumed that it pertains to other areas, ranging from musical intelligence to the interpersonal domain. Much of this book is an effort to call attention to the divergent considerations relevant to an understanding of the developmental course in more remote domains of intellect. For present purposes, however, this particular quarrel with Piaget can be suspended. We are now confronting development in that domain where Piaget's work remains supremely germane. Still, there are problems with the Piagetian perspective here as well. It has been well documented by now that development in the logical mathematical domain is less regular, lockstep, and stage-like than Piaget would have wished. Stages prove far more gradual and heterogeneous. Moreover, children show some signs of operational intelligence far earlier than Piaget had thought, while they fail to exhibit comprehensive formal operational thought even at the very height of their intellectual powers. The Piagetian picture of higher operational thought also applies principally to the mainstream of Western middle-class development. It is less relevant to individuals drawn from traditional or non-literate cultures, and also explains little about original research or path-breaking scientific work. What I wish to stress here is that Piaget did pose the right questions and achieve the crucial insights about the main factors involved in logical mathematical development. He shrewdly discerned the origins of logical mathematical intelligence in the child's actions upon the physical world. The crucial importance of the discovery of number, the gradual transition from physical manipulation of objects to interiorized transformations of actions, the significance of relations among actions themselves, and the special nature of higher tiers of development, where the individual begins to work with hypothetical statements and to explore the relationships and implications that obtain among those statements. To be sure, the realms of number, mathematics, logic, and science are not coextensive with one another, and, reflecting the views of many scholars, this chapter will treat differences in accent and coloration across these facets of logical mathematical intellect. But that they do form a family of interrelated competences seems to me true. One of Piaget's enduring contributions is to have suggested some of the integrating links. Other scholars in the areas of mathematics, logic, and science have also discerned and stressed the links between these domains of knowledge. The mathematician Brian Rotman indicates that the whole of contemporary mathematics takes for granted and rests on the notion of counting, on the interpretation that occurs in the message 1, 2, 3. The great 18th century mathematician Leonhard Euler underscored the importance of number as a basis for mathematical development. The properties of the numbers known today have been mostly discovered by observation, and discovered long before their truth has been confirmed by rigid demonstrations. We should use such discovery as an opportunity to investigate more exactly the properties discovered and to prove or disprove them. Or, in both cases, we may learn something useful. Willard Quine, perhaps the preeminent logician of the past half-century, indicates that logic is involved with statements while mathematics deals with abstract, non-linguistic entities, but that at its higher reaches logic leads by natural stages into mathematics. To be sure, numbers compose but a small part of mathematics at its highest levels. Mathematicians are interested more in general concepts than in specific calculations, seeking in fact to formulate rules that can apply to the widest possible range of problems. But as Whitehead and Russell sought to show, underlying even the most complex mathematical statements, one can find simple logical properties, the sorts of intuition that the child is beginning to display as his operational thinking unfolds. As Russell himself observed, logic and mathematics have had different histories, but in modern times have moved closer together. The consequence is that it has now become wholly impossible to draw a line between the two. In fact, the two are one. They differ as boy and man. Logic is the youth of mathematics, and mathematics is the manhood of logic. Whatever the views of the experts in these particular disciplines, then, it seems legitimate from the psychological point of view to speak of a family of interlocking capacities. Beginning with observations and objects in the material world, the individual moves toward increasingly abstract formal systems whose interconnections become matters of logic rather than of empirical observation. Whitehead put it succinctly: so long as you are dealing with pure mathematics, you are in the realm of complete and absolute abstraction. Indeed, the mathematician ends up working within a world of invented objects and concepts that may have no direct parallel in everyday reality, even as the logician's primary interests fall on the relationships among statements rather than on the relation of those statements to the world of empirical fact. It is primarily the scientist who retains the direct tie to the world of practice. He must come up with statements, models, and theories which, in addition to being logically consistent and susceptible to mathematical treatment, must also bear a justifiable and continuing relationship to facts which have been, and will be, discovered about the world. However, even these characterizations must be tempered. A scientific theory will often persist despite its inconsistency with certain empirical facts, and mathematical truths can themselves be altered based upon new discoveries in view of new demands placed on the characteristics of mathematical systems. While the products fashioned by individuals gifted in language and music are readily available to a wide public, the situation with mathematics is at the opposite extreme. Except for a few initiates, most of us can only admire from afar the ideas and works of mathematicians. Andrew Gleason, a leading contemporary mathematician, develops a telling figure of speech to portray this lamentable state of affairs. It is notoriously difficult to convey a proper impression of the frontiers of mathematics to non-specialists. Topology, the study of how space is organized, is like the great temples of some religions. That is to say, those uninitiated into its mysteries can view it only from the outside. Michael Polanyi, eminent scientist and philosopher, confessed that he himself lacked the necessary intellectual equipment to master many contemporary aspects of mathematics that those within the tribe would consider, as mathematicians are fond of saying, relatively trivial. One can glimpse the kinds of demand made in mathematical thinking by noting the difficulties in decoding this English sentence. We cannot prove the statement which is arrived at by substituting for the variable in the statement form. We cannot prove the statement which is arrived at by substituting in the statement form the name of the statement form in question, the name of the statement form in question. As Polanyi suggests, understanding this sentence may well require the setting up of a string of symbols, and then carrying out a set of operations upon these symbols. Clearly, the comprehension of certain strings of the symbols of language requires more than simple competence in linguistic syntax and semantics. Though it may be properly pointed out, such competences are a prerequisite for solving a sentence of this sort. In attempting to gain further insight into the thought processes of mathematicians, I, like many others, have found especially helpful the introspections of Henri Poincaré, one of the leading mathematicians in the world at the turn of the century. Poincaré raised the intriguing question why, if mathematics only involves the rules of logic, which are presumably accepted by all normal minds, anyone should have difficulty in understanding mathematics. To suggest an answer, he asks us to imagine a long series of syllogisms, where the conclusion of each one serves as the premise for the next. Because some time will elapse between the moment when we encounter a proposition at the conclusion of one syllogism and the time when we re-encounter it as the premise in the next syllogism, it is possible that several links of the chain may have unrolled, or we may have forgotten the proposition or changed it in some unrecognized way. If this ability to recall and use a proposition were the sine qua non of mathematical intelligence, then, Poincaré reasons, the mathematician would need to have a very sure memory or prodigious powers of attention. But many individuals skilled in math stand out neither for mnemonic nor for attentional powers, while a far larger group of individuals with keen memories or superb attentional span display little aptitude for mathematics. The reason the mathematician's memory does not fail him in a difficult piece of reasoning, Poincaré testifies, is because it is guided by reasoning. A mathematical demonstration is not simply a single juxtaposition of syllogisms. It is syllogisms placed in a certain order, and the order in which these elements are placed is much more important than the elements themselves. If I have the feeling, the intuition, so to speak, of this order, so as to perceive at a glance the reasoning as a whole, I need no longer fear lest I forget one of the elements, for each of them will take its allotted place in the array, and that without any effort of memory on my part. Poincaré distinguishes, then, between two abilities. One is sheer memory for steps in a chain of reasoning, which might well suffice for the recall of certain proofs. The other ability, and in his view by far the more important one, is an appreciation of the nature of the links between the propositions. If these links have been appreciated, the exact identity of the steps in the proof becomes less important, because if necessary, they can be reconstructed or even reinvented. We can observe this ability at work simply by trying to recreate Poincaré's own reasoning as just presented. If the drift of the argument has been grasped, its recreation proves a relatively simple matter. If one has not grasped the reasoning, however, one is consigned to falling back on literal verbal memory, which, even if it rescues an individual on a given occasion, is unlikely to exhibit much staying power. While the mental powers central to any field are spread out unequally within the population, there are few fields of endeavor where the extremes are so great, and the importance of generous initial endowment so patent. As Poincaré points out, the capacity to follow the chain of reasoning is not that elusive, but the ability to invent significant new mathematics is rare. Anyone could make new combinations with mathematical entities. To create consists precisely in not making useless combinations, and in making those which are useful, and which are only a small minority. Invention is discernment, choice. Among chosen combinations, the most fertile will often be those formed of elements drawn from domains which are far apart. According to Alfred Adler, a mathematician who has introspected tellingly upon the trials and the triumphs of his field, almost no one is capable of doing significant mathematics. There is no acceptably good mathematics. Each generation has its few great mathematicians, and mathematics would not even notice the absence of the others. In mathematics, those with true genius are discovered virtually immediately and, in comparison with other disciplines, there is little energy wasted in jealousy, bitterness, or reservation, because the characteristics of the mathematically blessed are so evident. What characterizes those with mathematical gifts? According to Adler, the powers of mathematicians rarely extend beyond the boundary of the discipline. Mathematicians are seldom talented in finance or the law. What characterizes the individual is a love of dealing with abstraction, the exploration, under the pressure of powerful implosive forces, of difficult problems for whose validity and importance the explorer is eventually held accountable by reality. The mathematician must be absolutely rigorous and perennially skeptical. No fact can be accepted unless it has been proved rigorously by steps that are derived from universally accepted first principles. Mathematics allows great speculative freedom. One can create any kind of system that one wants. But in the end, every mathematical theory must be relevant to physical reality, either in a straightforward manner or by relevance to the main body of mathematics, which in turn has direct physical implications. What sustains and motivates the mathematician is the belief that he may be able to create a result that is entirely new, one that changes forever the way that others think about the mathematical order. A great new mathematical edifice is a triumph that whispers of immortality. Adler's sentiments echo those of a renowned mathematician of an earlier generation, G.H. Hardy. It is undeniable that a gift for mathematics is one of the most specialized talents, and that mathematicians as a class are not particularly distinguished for general ability or versatility. If a man is in any sense a real mathematician, then it is 100 to 1 that his mathematics will be far better than anything else he can do. And he would be silly if he surrendered any decent opportunity of exercising his one talent in order to do any undistinguished work in other fields. Like a painter or poet, a mathematician is a maker of patterns. But the special characteristics of mathematical patterns are that they are more likely to be permanent because they are made with ideas. A mathematician has no materials to work with, and so his patterns are likely to last longer since ideas erase less well than words do. Comments Hardy? Quite possibly the most central and least replaceable feature of the mathematician's gift is the ability to handle skillfully long chains of reasoning. If a biologist were to study the locomotive processes of an amoeba and then try to apply his conclusions to successive levels of the animal kingdom, ending up with a theory of human walking, we might think him eccentric. Yet, as Andrew Gleason has pointed out, the mathematician regularly does just this sort of thing. He applies in very complicated contexts theories that were derived in very simple ones, and he generally expects that the results will be valid, not merely in outline, but in detail. Initially, this prosecution of an extended line of reasoning may be intuitive. Many mathematicians report that they sense a solution or a direction long before they have worked out each step in detail. Stanislaw Ulam, a contemporary mathematician, reports, "If one wants to do something original, it is no longer a case of syllogism chains. One is only occasionally aware of something in the brain which acts as a summarizer or totalizer of the process going on, and that probably consists of many parts acting simultaneously." Poincaré speaks of mathematicians who are guided by intuition and, at first stroke, make quick but sometimes precarious conquests like bold cavalrymen of the advance guard. But eventually, if the mathematics is to convince others, it must be worked out in precise detail, with nary an error in definition or in chain of reasoning. And this Apollonian aspect is essential to the performance of the mathematician. In fact, either errors of omission, forgetting a step, or of commission, making some assumption that is unnecessary, can destroy the value of a mathematical contribution. The launching of a field of study, or if you will, a science of mathematics, occurs when the findings of each generation build upon those of the last. In earlier times, it was possible for an educated person to follow mathematical thinking pretty much up to the contemporary moment. But for at least a century, this has not been possible. It is notable that while the cultural domains that invoke different intelligences all continue to develop, few, if any, have evolved in so arcane a way as has logical mathematical thought. In fact, in a manner paralleling the individual developmental pattern I have sketched, mathematics has become increasingly abstract with the years. Alfred Adler traces this course. The first abstraction is the idea of number itself, and the idea that different quantities can be distinguished from one another on that basis. Every human culture has made this step. Next comes the creation of algebra, where numbers are regarded as a system, and one can introduce variables to take the place of particular numbers. The variables, in turn, are simply specialized cases of the more generalized dimension of mathematical functions, where one variable has a systematic relation to another variable. These functions need not be restricted to real values, such as lengths or widths, but can confer meaning upon other functions, upon functions of functions, and upon even longer strings of reference as well. In short, as Adler indicates, by abstracting and generalizing first the concept of number, then the concept of the variable, and finally that of the function, it is possible to arrive at an extremely abstract and general level of thought. Naturally, with each further step in the ladder of abstraction, some individuals will find the sequence too difficult, too painful, or insufficiently rewarding, and hence will drop out. It ought to be pointed out that there is also in mathematics a powerful pull toward finding simpler expressions and for returning to the fundamental notions of numbers. Therefore, there may be a place in the discipline of mathematics for individuals who are not especially gifted in following through these long chains of reasoning, or these increasingly abstract tiers of analysis. To choose life as a mathematician would seem a difficult move. It is not surprising that mathematicians seem, to an outsider, to be chosen by their precocious skills in the numerical realms, and by their singular passion for abstraction. The world of the mathematician is a world apart, and one must be ascetic to derive sustenance from it. The imperative to concentrate energies for many hours on seemingly intractable problems is the norm, and casual contacts with other individuals cannot be allowed to attain much importance. Language is also not much help. One is on one's own with pencil and paper and one's own mind. One must think very hard, and thus one often suffers severe strain, if not a breakdown. But mathematics can also provide protection against anxiety. As Stanislaw Ulam suggests, a mathematician finds his own monastic niche and happiness in pursuits that are disconnected from external affairs. In their unhappiness over the world, mathematicians find a self-sufficiency in mathematics. If the isolation is severe and the concentration demanding and painful, the rewards seem to be of high order indeed. Mathematicians who have introspected about their feelings upon solving a difficult problem regularly stress the exhilaration that accompanies the moment of breakthrough. Sometimes the intuition comes through first, and then one must actually make efforts to work through the details of the solution. At other times, the careful execution of the steps actually suggests the solution. Less frequently, intuition and discipline arrive at the same time or work in concert. But whatever its mode, the solving of a difficult and important problem, and this is the only problem that mathematicians feel worthy of their energy, unless it be to demonstrate that a problem cannot in principle be solved, provides a thrill of a very special sort. But what excites mathematicians? One obvious source of delight attends the solution of a problem that has long been considered insoluble. Inventing a new field of mathematics, discovering an element in the foundation of mathematics, or finding links between otherwise alien fields of mathematics are certainly other rewards. In fact, the ability not merely to discover an analogy, but to find an analogy between kinds of analogies has been singled out as an especial mathematical delight. And it seems that dealing with elements that are counterintuitive provides yet another special kind of gratification for mathematicians. Roaming in the realm of imaginary numbers, irrational numbers, paradoxes, possible and impossible worlds having their own peculiar properties, yields yet other delicacies. It is possibly not an accident that one of the outstanding inventors of a world, contrary to fact, Lewis Carroll, was also a first-rate logician and mathematician. The tribe of mathematicians is sufficiently special and sufficiently remote that it is tempting to lump all its members together. However, within the discipline, individuals readily rate and contrast one another. Speed and power of abstraction provide an immediate means of ranking and, quite possibly, the one that matters above all else. It is paradoxical that in mathematics there is still no Nobel Prize, because it is probably the single human intellectual endeavor in which consensus about distribution of talent is the greatest among its practitioners. But other dimensions as well are often invoked in discussions of mathematical skill. For instance, some mathematicians are much more given to the use and the valuing of intuition, while others extol only systematic proof. Nowadays, mathematicians are fond of assessing the greatest mathematician of the previous generation, John von Neumann. In such evaluations, relevant criteria include the ability to size up an area and decide whether it harbors interesting problems, the courage to take on difficult and seemingly intractable problems, and the ability to think extremely rapidly. In discussing von Neumann, whom he knew well, Ulam comments, "As a mathematician, von Neumann was quick, brilliant, efficient, and enormously broad in scientific interest beyond mathematics itself. He knew his technical abilities, his virtuosity in following complicated reasoning, and his insights were supreme. Yet he lacked absolute self-confidence. Perhaps he felt that he did not have the power to divine new truths intuitively at the highest level, or the gift for a seemingly irrational perception of proofs or formulation of new theorems. Perhaps it was because on a couple of occasions he had been anticipated, preceded, or even surpassed by others. In other words, von Neumann was the master of, but also a little bit the slave to, his own technical skill." Further insight into von Neumann's powers comes from a recollection of Jacob Bronowski, himself trained as a mathematician. Von Neumann was trying to explain a finding to Bronowski, who could not grasp the point. "Oh no," said von Neumann, "you are not seeing it. Your kind of visualizing mind is not right for seeing this. Think of it abstractly. What is happening on this photograph of an explosion is that the first differential coefficient vanishes identically, and that is why what becomes visible is the trace of the second differential coefficient." The engineer Julian Bigelow recalls, "Von Neumann was a fantastic craftsman of theory. He could write a problem out the first time he heard it, with a very good notation to express the problem. He was very careful that what he said and what he wrote down was really exactly what he meant." According to historian of mathematics Steve Himes, this ability to write down a problem in proper notation indicates that, regardless of the content of a problem, von Neumann was immediately concerned with form. Thus, he demonstrated a power of intuition denied to his colleagues, one of whom said, beyond anyone else, he could almost instantly understand what was involved and show how to prove the theorem in question, or to replace it by what was the true theorem. Ulam compares himself to other mathematicians, including, it would seem, von Neumann, when he says, "As for myself, I cannot claim that I know much of the technical material of mathematics. What I may have is the feeling for the gist, or maybe only the gist of the gist, in a number of its fields. It is possible to have this knack for guessing or feeling what is likely to be new or already known, or else not known in some branch of mathematics, where one does not know the details. I think I have the ability to a degree and can often tell whether a theorem is known, i.e., already proved, or is new conjecture." Ulam adds an interesting aside on the relation between this skill and the musical faculty. "I can remember tunes and am able to whistle various melodies rather correctly. But when I try to invent or compose some new, catchy tune, I find rather impotently that what I do is a trivial combination of what I have heard." This is in complete contrast to mathematics, where I believe, with a mere touch, I can always propose something new. It seems evident that mathematical talent requires the ability to discover a promising idea and then to draw out its implications. Ulam can accomplish this feat readily in mathematics, but lacks the ability almost totally in the musical sphere. In contrast, Arthur Rubinstein, one of our guides to the area of music, utters the opposite complaint. For him, mathematics is impossible. At the center of mathematical prowess lies the ability to recognize significant problems and then to solve them. As for what permits recognition of promising problems, mathematicians seem at a loss. The context of discovery remains a mystery, although, as in music, it is clear that some technically gifted individuals are immediately drawn to discovery and have a flair for it, while others of equal or even greater technical competence lack this particular bent. In any event, a considerable literature has developed on methods of problem solving. Mathematicians have devised various heuristics that help individuals to solve problems, and informal training in mathematics often involves assimilating and passing on these techniques to the next generation. From students of mathematical problem solving like George Polya, Herbert Simon, and Alan Newell, one picks up pointers. Mathematicians are advised to generalize, to proceed from the given set of objects in a problem to a larger set that contains the given one. Conversely, mathematicians are also advised to specialize, to pass from a given set of objects to a smaller set, itself contained in the given one. To ferret out analogies, thereby finding a problem or a situation that bears instructive similarities and differences from the one under consideration. Other procedures are frequently mentioned. Faced with a problem too complex or unwieldy to solve, the mathematician is counseled to find a simpler problem within the larger one, to seek a solution to the simpler component, and then to build upon that solution. The student is also advised to propose a possible solution and to work backward to the problem, or to describe the characteristics that a solution should have, and then, in turn, to try to attain each of them. Another popular method is indirect proof. One assumes the opposite of what one is trying to prove and ascertains the consequence of that assumption. More specific heuristics exist and are drawn upon within particular areas of mathematics. Clearly, because the most interesting problems are difficult to solve, the mathematician who can draw upon these heuristics appropriately and shrewdly is at a decided advantage. Perhaps the ability to learn and to deploy such heuristics, to supplement purely logical considerations with a sense of what might work, helps define the zone of proximal development in the aspiring mathematician. Though many mathematicians highly value their intuition, these explicit methods of problem solving are their stock in trade, what they fall back on when inspiration and intuition fail. But these heuristics are not exclusively the possession of the mathematician. Indeed, they prove equally useful to individuals involved in problem solving in other areas of life, and serve as one way of connecting the activities of that rare bird, the pure mathematician, to the pursuits of the others. In particular, they help illuminate the lot of the practicing scientist who must also pose and then solve problems in the most efficient and effective way. Certainly, science and mathematics are closely allied. The progress, even the invention of science, has been linked to the status of mathematics during particular historical epochs, and practically every significant mathematical invention has eventually proved useful within the scientific community. To cite just a few examples, the Greek study of conic sections in 200 BC made possible Johannes Kepler's laws of planetary motion in 1609. More recently, David Hilbert's theory of integral equations was needed for quantum mechanics, and Georg Friedrich Riemann's differential geometry proved basic for the theory of relativity. Indeed, the marked progress of Western science since the 17th century can be traced to a significant extent to the invention of differential and integral calculus. Chemistry and physics are concerned with explaining change, the evolution of physical systems, and not the description of steady states. Without the calculus, the process of dealing with such changes could be very difficult because one would have to calculate every tiny step of the process. But with the calculus, it is possible to determine how the change of one quantity relates to other quantities connected to it. It is thus fitting that Newton, one of the inventors of the calculus, had the opportunity to work out the motion of the planets. The scientist needs mathematics because the body of brute fact is unwieldy. The orderly scheme of abstract relations that he can obtain from mathematics is a chief tool in making some order out of this chaos. Yet the core of the fields of science, for example physics, and mathematics can be clearly distinguished. Whereas the mathematician is interested in exploring abstract systems for their own sake, the scientist is motivated by a desire to explain physical reality. For him, mathematics is a tool, albeit an indispensable one, for building models and theories that can describe and eventually explain the operation of the world, be it the world of material objects, physics and chemistry, of living things, biology, of human beings, social or behavioral sciences, or of the human mind, cognitive science. In classical times, science was closely tied with philosophy, from which it took its questions, and with mathematics, whose methods were often devised in the course of attempting to resolve specific questions. With the passage of time, however, the enterprise of science has become increasingly independent, though it continues to cross-fertilize with philosophy and mathematics. Among the factors important in the rise of science as a separate and, nowadays, increasingly splintered enterprise have been its dissociation from politics and theology. The increasing reliance on empirical observation, measurement, and crucial experiments designed to test one model or theory against another. And the rise of published scientific reports where claims are written out and procedures detailed so that other individuals have the opportunity to replicate studies, to criticize them, and to carry out their own further line of investigation in an effort to support, reformulate, or undermine the scientific dogma of their time. As Piaget noted long ago, the evolution of science here displays certain intriguing parallels with the development in children of logical mathematical thought. In both cases, we find simple experimentation with objects and the noting of their patterns of interaction and behavior to be the earliest and most basic procedure. The practice of making careful measurements, devising statements about the way in which the universe works, and then subjecting these statements to systematic confirmation does not occur until relatively late in the evolution of the individual and at a comparably tardy moment in the evolution of scientific thought. We can observe as well a series of stages in the advent of modern science. First, early in the 17th century, Francis Bacon stressed the importance of systematic accumulation of facts. However, given his ignorance of mathematics and his failure to pose pregnant questions, Bacon's contribution remained more programmatic than substantive. Shortly afterward, Galileo championed the introduction of mathematics into scientific work. He argued against the simple recording of colors, tastes, sounds, and smells, and pointed out that these elements would not even exist were it not for the particular sense organs with which individuals happen to be endowed. Yet even Galileo's introduction of structured techniques of measurement into the scientist's arsenal did not suffice to usher in the modern era. To do so was left to Isaac Newton, an incomparable thinker who, in explicit formal operational style, made a comprehensive survey of physical findings and, applying both analysis and synthesis, fitted together the various pieces into a coherent pattern. As the historian of science Herbert Butterfield put it, one youth who made a comprehensive survey of the field and possessed great elasticity of mind could place the pieces into the proper pattern with the help of a few intuitions. In a manner that cannot fail to please Piagetians, Newton postulated an absolute framework of time and space, within which physical events unfold according to a set of immutable laws. Though scientific and mathematical talent may reside in the same individual, for example in Newton, the motives behind scientists' passions do not much resemble those we encountered in the lives of mathematicians. What seemed more than anything else to impel Newton the scientist was desire to find the secrets or the secret of nature. Newton himself knew it was too difficult to explain all of nature, but he did share the notion of being an explorer. I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting himself and then finding a smoother pebble or a prettier shell than ordinary, while the greater ocean of truth lay all undiscovered before me. Bronowski comments on the pleasure attending a discovery by the scientist. When the figures come out right like that, you know, as Pythagoras did, that a secret of nature is open in the palm of your hand. A universal law governs the majestic clockwork of the heavens, in which the motion of the moon is one harmonious incident. It is a key that you have put into the lock and turned, and nature has yielded in numbers the confirmation of her structure. The desire to explain nature rather than to create a consistent, abstract world engenders an instructive tension between pure scientists and pure mathematicians. The mathematician may peer down his nose at scientists for being practical, applied, insufficiently interested in the pursuit of ideas for their own sake. The scientist, in turn, may feel that the mathematician is out of touch with reality and tends to pursue ideas forever, even when, or perhaps even especially when, they do not lead anywhere and may not be of practical consequence. These ideal-real prejudices aside, the talents rewarded by the two fields also seem different. For the mathematician, it is most important that one recognize patterns wherever they may exist, that one be able to carry out the implications of one's train of thinking wherever they may lead. For the scientist, a healthy planting of one's feet on the ground and perpetual concern with the implication of one's ideas for the physical universe is a needed and useful feature that goes beyond the mathematician's burden. As Albert Einstein, who considered both careers, put it, truth in physical matters can, of course, never be founded on mathematical and logical considerations alone. And he reminisced illuminatingly on his own career decision. The fact that I neglected mathematics to a certain extent had its cause, not merely in my stronger interest in science than in mathematics, but also in the following strange experience. I saw that mathematics was split up into numerous specialties, each of which could easily absorb the short lifetime granted to us. This was obviously due to the fact that my intuition was not strong enough in the field of mathematics. In physics, however, I soon learned to scent out that which was able to lead to fundamentals and to turn aside from everything else, from the multitude of things that clutter up the mind and divert it from the essential. Just what is the nature of the intuitions that characterize outstanding scientists, ones of the caliber of a Newton and an Einstein? Beginning with an absorbing interest in the objects of the world and how they operate, these individuals eventually enter into a search for a limited set of rules or principles that can help to explain the behavior of objects. The greatest progress is made when disparate elements are linked, and a few simple rules can explain observed interactions. Conceding that this ability differs from the analogizing powers of the pure mathematician, Ulam confesses that it is difficult for the mathematician to understand what it means to have an intuition for the behavior of physical phenomena. He suggests, in fact, that few mathematicians actually have this intuition. Werner Heisenberg, himself a Nobel laureate in physics at the age of 32, recalls the physical intuitions of his mentor, Niels Bohr, and how they often overran what the latter could prove. Bohr must surely know that he starts from contradictory assumptions, which cannot be correct in their present form. But he has an unerring instinct for using these very assumptions to construct fairly convincing models of atomic processes. Bohr uses classical mechanics or quantum theory that way, just as a painter uses his brush and colors. Brushes do not determine the picture, and color is never the full reality. But if he keeps the picture before his mind's eye, the artist can use his brush to convey, however inadequately, his own mental picture to others. Bohr knows precisely how atoms behave during light emission, in chemical processes and in many other phenomena, and this has helped him to form an intuitive picture of the structure of different atoms. It is not at all certain that Bohr himself believes that electrons revolve inside the atom, but he is convinced of the correctness of his picture. The fact that he cannot yet express it by adequate linguistic or mathematical techniques is no disaster. On the contrary, it is a great challenge. Such faith in the power of one's own intuitions concerning the ultimate nature of physical reality recurs over and over again in the introspections of the physicists. In speaking to Einstein, Heisenberg once said, "I believe, just like you, that the simplicity of natural laws has an objective character, that it is not just the result of thought economy. If nature leads us to mathematical forms of great simplicity and beauty, by forms I am referring to coherent systems of hypotheses, actions, etc., to forms that no one has previously encountered, we cannot help think that they are true, that they reveal a genuine feature of nature. But the mere fact that we could never have arrived at these forms by ourselves, that they were revealed to us by nature, suggests strongly that they must be part of reality itself, not just our thoughts about reality. I am strongly attracted by the simplicity and beauty of the mathematical schemes with which nature presents us. You must have felt this too. The almost frightening simplicity and wholeness of the relationships which nature suddenly spreads out before us, and for which none of us was in the least prepared. It is left to the greatest scientists to pose questions that no one has posed before, and then to arrive at an answer that changes for all time the way in which scientists, and eventually laymen, construe the universe. Einstein's genius lay in his persistent questioning of the absoluteness of time and space. Already as a teenager, Einstein pondered what our experience would be like if we ourselves were operating from the point of view of light, or, to put it more concretely, if we rode on a beam of light. Suppose, he asked, that we were looking at a clock, but were flying away from it at the speed of light. The time on the clock would then be frozen because a new hour could never travel fast enough to catch up with us. On the beam of light, the time of that clock would remain perpetually the same. Einstein came to think that, as one approximated the speed of light, one became increasingly isolated in his box of time and space, and departed increasingly from the norms around him. No longer was there such a thing as universal time. Indeed, the experience of time would now become different for the traveler on the beam from what it was for the individual remaining at home. However, one's experiences on the beam of light are consistent with each other. The same relations among the time, distance, speed, mass, and force that Newton had described continue to obtain on that beam, and they continue to obtain with a similar consistency in the region of the clock. It is just that the actual values produced for time, distance, and the like are no longer identical for both the beam traveler and the individual who has remained in the vicinity of the clock. To follow through this line of thinking, to reconcile it with findings of the past, like the Michelson-Morley experiment that challenged the existence of the medium of ether, and with hypothetical future experiments, and then to write out the mathematics needed to create a theory of relativity, took Einstein years and constitutes part of the history of our times. What should be remarked upon here is that his scientific originality lay in the boldness of conceiving the problem, in the persistence in carrying it through with all of its mystifying and unsettling implications, and in the subtlety to appreciate its connection to the most basic questions about the nature and structure of the universe. Einstein required courage to execute this line of thinking on his own for years, despite the fact that it flouted conventional wisdom, and to believe that his resulting description might be truly more simplifying, edifying, and comprehensive, hence more true, than Newton's universally accepted synthesis of 2 centuries before. As the physicist Gerald Holton has persuasively argued, such a program requires more than just technical facility, mathematical acuity, and keen observational powers. Though each of these is probably a prerequisite, scientists are also guided by underlying themes of themata, beliefs about how the universe must work, and basic convictions about how these principles are best revealed. In Einstein's case, the very belief that there will be a few simple laws, that they will unify diverse phenomena, and that there will be no element of chance or indeterminacy in these laws, are part and parcel of his professional code. Einstein is said to have remarked, God wouldn't have passed up the opportunity to make nature this simple. Themata such as these may at times be more central to discussion than the objective facts and figures that are the scientist's normal stock in trade. As Holton puts it, the awareness of themata, which are sometimes held with obstinate loyalty, help one to explain the character of the discussion between antagonists far better than do scientific content and social surroundings alone. The discussion of themes situated at the core of a scientist's system brings to the fore a puzzling but central aspect of scientific practice. Even though the scientist's self-image nowadays highlights rigor, systematicity, and objectivity, it seems that in the final analysis, science itself is virtually a religion, a set of beliefs that scientists embrace with a zealot's conviction. Scientists not only believe in their methods and themes from the depth of their being, but many are also convinced it is their mission to use these tools to explain as much of reality as falls within their power. This conviction is perhaps one of the reasons that the great scientists have typically been concerned with the most cosmic questions, and that, particularly in the latter years of life, they are often given to making pronouncements about philosophical issues, such as the nature of reality or the meaning of life. Even Newton, it has recently been documented, devoted much of his lengthy life to a consideration of diverse aspects of mysticism, metaphysics, and cosmology, and put forth many views that would strike us today as medieval, if not wholly bizarre. Underlying this interest, it seems to me, is much the same desire to explain the world that comes through in a more constrained and disciplined fashion in physics. Commentator Frank Manuel has expressed it this way: Newton's statement of fundamental religious principles, his interpretation of prophecy, his textual criticism of the historical words of Scripture, his system of world chronology, his cosmological theories, and his euhemeristic reduction of pagan mythology all bespeak the same mentality and style of thought. As nature was consonant with itself, so was Isaac Newton's mind. At the height of his powers, there was in him a compelling desire to find order and design in what appeared to be chaos. To distill from a vast inchoate mass of materials a few basic principles that would embrace the whole and define the relationships of its component parts. In whatever direction he turned, he was searching for a unifying structure. Here, certainly, we see divergence from the concerns of most mathematicians, who would just as soon turn their backs on reality as try to encompass within their equations and theorems all of its complexity and messiness. And this passion for the single unifying explanation made to mark a line between the physical sciences and other disciplines as well. While individuals in other sciences are certainly drawn to explanations of their reality, be it biological, social, or cognitive, they are less likely to search for the overall explanations of the essence of life. And others of a strong logical mathematical ability, for example chess players, are also unlikely to devote much energy to a search for the secret of the world's powers. Perhaps, though just perhaps, the desire to solve the principal philosophical puzzles of existence is a special feature of the childhood of the young physical scientist. As a child of 4 or 5, Albert Einstein received a magnetic compass. He was awed by the needle, isolated and unreachable, yet seemingly caught in the grip of an invisible urge that attracted it toward the north. The needle came as a revelation, for it challenged the child's tentative belief in an orderly physical world. I can still remember, or at least I believe I remember, that this experience made a deep and abiding impression on me. It is risky to make too much of a single childhood memory, and Einstein, ever careful with his thoughts and words, encircles his own uncertainty by the telltale phrase, "I believe I remember." Yet it is instructive to compare Einstein's recollections of a pivotal early experience with those of other individuals in the logical mathematical field. An example: our mathematical guide Stanislaw Ulam recalls that, as a young child, he was fascinated by the intricate patterns in an oriental rug. The resulting visual picture seemed to produce a melody with relations among the various parts resonating with one another. Ulam speculates that such patterns feature a kind of inherent mathematical regularity and power to which certain young individuals are particularly sensitive. And such sensitivity may rely in large measure on a kind of keen memory that enables the child to compare a presently perceived pattern, be it primarily visual or merely ordered, with others operated upon in the past. As an aside, I might mention that in our observations of young children, my colleagues and I have identified a group of youngsters who are especially attracted to, if not fixated upon, repetitive patterns. Then, unaware of Ulam, we nicknamed these children patterners and contrasted them with another group, presumably more linguistically oriented, whom we termed dramatists. Of course, we do not yet know whether children dubbed patterners in their youth are more at risk to become mathematicians, and other childhood attractions for those in the logical mathematical field. As a youth, Pascal was avid to learn about mathematics, but was kept from doing so by his father, who in fact forbade him to speak about mathematics. Pascal, however, began to dream about the subject, and he used to mark with charcoal the walls of his playroom, seeking a means of making a circle perfectly round and a triangle whose sides and angles were all equal. He discovered these things for himself and then began to seek the relationship which existed between them. He did not know any mathematical terms, and so he made up his own. Using these names, he made axioms and finally developed perfect demonstrations until he had come to the 32nd proposition of Euclid. Bertrand Russell recalls, "I began Euclid with my brother as my tutor at the age of 11. It was one of the great events of my life, as dazzling as first love. I had not imagined that there was anything as delicious in the world from that moment until I was 38. It was my chief interest and my chief source of happiness. Mathematics is not human and has nothing particular to do with this planet or with the whole accidental universe. Because like Spinoza's God, it won't love us in return." Ulam offers one possible account of the course of such passions. At first, a young child undergoes some satisfying experiences with numbers. Then he experiments further and builds up his store and memory of experiences in the numerical and symbolic domains. Eventually, the child proceeds beyond his own idiosyncratic, though sometimes universally shared, explorations, his natural mathematical curiosity, to an acquaintance with problems that have in the past challenged mathematicians. If he is to achieve much, he must then spend hours each day thinking about these issues. For the bald fact is that, in mathematics more so than in any other intellectual domain, the years of the third and the fourth decades of life are crucial. The ability to store and manipulate within one's mind, during a finite period of time, all the variables necessary to make progress on important mathematical problems is one that, for one or another, presumably neurological reason, proves especially vulnerable to age, even as young an age as 30 or 40. It is a difficult and often tormenting assignment. Still another childhood journey surrounds the contemporary American philosopher and logician Saul Kripke, reputed to be the most brilliant philosopher of his generation. At age 3, young Saul went to see his mother in the kitchen and asked her if God were truly everywhere. Receiving an affirmative answer, he then asked whether he had squeezed part of God out of the kitchen by coming in and taking out some of the space. Befitting a mathematical prodigy, Kripke went forth quickly on his own, and had reached the level of algebra by the time he was in 4th grade. For instance, he discovered that in multiplying the sum of two numbers by the difference between them, he got the same answer as he did when he subtracted the square of the smaller one from the square of the larger number. Once he realized that this pattern applied to any set of numbers, he had arrived at the core of algebra. Kripke once mentioned to his mother that he would have himself invented algebra if it had not already been invented, because he came upon its insights so naturally. This ability to devise areas of study may be common among prodigious young mathematicians. The great Descartes said, "As a young man, when I heard about ingenious inventions, I tried to invent them by myself, even without reading the author." Such biographical notes confirm that talent in the logical mathematical sphere announces itself very early. Initially, the individual can proceed rapidly on his own, as it were, almost apart from experience. Perhaps individuals with this general talent might, by an accident of history, be directed randomly to mathematics, logic, or physics. My own guess is that careful study might uncover different telltale early experiences in individuals. The physicist may be especially intrigued by physical objects and their operations. The mathematician may be immersed in patterns per se. The philosopher will be intrigued by paradoxes, by questions about ultimate reality, and by the relationships among propositions. Of course, whether this affinity is in itself accidental, or whether each individual gravitates toward those objects or elements for which he has certain proclivities, is a riddle I had better leave to someone of a more decidedly logical mathematical bent. Whatever the precocity of the young logician mathematician, it is crucial that he advance quickly in his field. As we have seen, the best years for productivity in these fields are before the age of 40, maybe even before the age of 30. And while solid work can be conducted after that time, it seems relatively rare. G. H. Hardy says, I write about mathematics because, like any other mathematician who has passed 60, I have no longer the freshness of mind, the energy, or the patience to carry on effectively with my proper job. Rabi, Nobel laureate physicist, observes that younger individuals carry the baton in his field because they have vast physical energy. Queried about what age physicists tend to run down, he says, it very much depends on the individual. I've seen people run down at 30, at 40, at 50. I think it must be basically neurological or physiological. The mind ceases to operate with the same richness and association. The information retrieval part sort of goes along with the interconnections. I know that when I was in my late teens and early 20s, the world was just a Roman candle. Rockets all the time. You lose that sort of thing as time goes on. Physics is an otherworld thing. It requires a taste for things unseen, even unheard of, a high degree of abstraction. These faculties die off somehow when you grow up. Profound curiosity happens when children are young. I think physicists are the Peter Pans of the human race. Once you are sophisticated, you know too much. Far too much. Wolfgang Pauli once said to me, I know a great deal. I know too much. I am a quantum ancient. In mathematics, the situation may be even more severe. Alfred Adler says that the major work of most mathematicians is over by the age of 25 or 30. If little has been accomplished by that time, little is likely to be accomplished in the future. Productivity drops off with each decade, and what is known with difficulty by the teacher is picked up easily, sometimes even effortlessly, by the students. This leads to a kind of poignant technological unemployment, where even the greatest mathematicians are doomed, like young swimmers or runners, to spending most of their self-conscious lives burdened with the knowledge that they have passed their primes. This situation contrasts with that found in many humanistic areas of scholarship, where major works typically appear during the fifth, the sixth, or the seventh decades of life. As we have seen, the ability to calculate rapidly is at best an accidental advantage for mathematicians. Certainly, it is far from central to their talent, which must be of a more general and abstract variety. There are, however, selected individuals who have an ability to calculate enormously well, and one can see in them a portion of logical mathematical ability operating in relatively autonomous form. Probably the chief examples of this profile are idiot savants, individuals who, with meager or even retarded abilities in most areas, display from early childhood an ability to calculate very rapidly and very accurately. The human calculator has learned a set of tricks. He can add large numbers in his head, commit to memory long sequences of numbers, perhaps state the day of the week for any randomly chosen date in the last 3 centuries. It must be stressed that these individuals typically are not interested in discovering new problems, or in solving venerable old ones, or even in observing how other people have solved them. Idiot savants do not seek to use mathematics to help them in other areas of daily life, or to tackle scientific puzzles. Instead, they have mastered a series of maneuvers that enable them to stand out, like freaks. There are exceptions. The mathematician Carl Friedrich Gauss and the astronomer Truman Safford were outstanding calculators, but in general, this talent is most salient in other wise, unremarkable persons. In most cases, the idiot savant appears to have a genuine calculating ability, one that sets him apart from an early age. For example, an institutionalized child named Obadiah taught himself at the age of 6 to add, subtract, multiply, and divide. George, a calendar calculator, was discovered poring over the perpetual calendar in an almanac at age 6, and almost from the beginning, proved completely accurate in his calendar calculation. L, an 11-year-old who was studied by the neurologist Kurt Goldstein, was able to remember virtually endless series, such as railroad timetables and newspaper financial columns. From an early age, this youngster had delighted in counting objects and had shown remarkable interest in all aspects of numbers and of musical sounds. In other cases, however, there seems to have been no great skill or promise to begin with. Rather, being relatively more skilled at this particular pursuit than at others, an otherwise hapless individual invested considerable energy in achieving one particular island of superiority over other individuals. Should this speculation be valid, it might be possible to take individuals with otherwise crippling deficits and train them to achieve such mathematical facility. My own guess, however, is that early arithmetical or calendrical prodigiousness is based upon the relative sparing or proliferation of certain brain areas. Like hyperlexia, it represents an automatic, impossible-to-stop process, rather than one that comes about because of excessive application in a casually chosen domain of potential expertise. Even as certain individuals appear blessed with at least one core component of logical mathematical aptitude, those of otherwise normal abilities show selective weakness in the numerical realm. Some of these may well have a selective numerical difficulty, akin to the difficulties exhibited by many children with written language, dyslexics, and by a far smaller number with spoken language, dysphasics. The most intriguing manifestation of this disability occurs in individuals diagnosed as having the developmental Gerstmann syndrome. Patterned after an adult syndrome of the same name, youngsters with this condition exhibit isolated impairment in learning arithmetic. Along with difficulties in recognizing and identifying fingers and in distinguishing their left from right. Though there may be selective problems in writing or spelling, language is normal in these children. This is how we know they are not generally retarded. Neurologists have speculated that these individuals have a deficiency in those regions, the association cortexes in the posterior areas of the dominant hemisphere, that are involved in recognizing ordered arrays and patterns in the visual sphere. According to the prevailing analysis, such selective difficulty with order, especially of a visual spatial sort, can at one swoop bring about problems in finger recognition, left-right orientation, and numerical calculation. The fact that most children begin their numerical calculations by using fingers confers an especially intriguing flavor upon this exotic syndrome. There may be other children who also exhibit selective difficulties in logical mathematical thinking. In those cases where the problem is not simply or complexly motivational, the difficulty may inhere in understanding principles of causality or strings of logical implication, which become vital in mathematics once one has passed the stage of simple counting and elementary calculation. As the educator John Holt has questioned, somewhat plaintively, what must it be like to have so little idea of the way the world works, so little feeling for the regularity, the orderliness, the sensibleness of things? Stranded at the opposite end of the continuum from the future physicists, such youngsters not only have no desire to find out the secrets of the world's orderliness, but may not even detect such order as does manifestly exist for others. In comparison with language and even with music, we know little about the evolutionary antecedents of numerical ability, and a comparatively minimal amount about its organization in the brain of the normal human adult of today. There are certainly, in other animals, precursors of numerical ability. These include the abilities of birds to recognize arrays of up to 6 or 7 objects reliably, the instinctive ability of bees to calculate distances and directions by observing the dance of their conspecifics, and the capacity of primates to master small numbers and also to make simple estimates of probability. Calendars and other notational systems go back at least 30,000 years, well before the existence of written language. The former way of ordering one's life was certainly available to individuals during the later Stone Age. Our ancestors must have possessed the principal insight of number as an endless sequence where one could continually add one to make a larger unit. Thus, they were not restricted to the small set of perceptibly accessible numbers that seems to be the limit for infrahuman organisms. As for the organization of numerical abilities in the brain, there are clearly individuals who lose the ability to calculate while remaining linguistically intact, as well as a far larger set of cases of individuals who are aphasic but can still make change, play games requiring calculation, and manage their financial affairs. As was the case with language and music, language and calculation at even the most elementary level prove to be quite separate. Moreover, as evidence accumulates, we are finding, shades of music once again, that important aspects of numerical ability are normally represented in the right hemisphere. Most observers agree that there can be a breakdown of separate arithmetical abilities, comprehending numerical symbols, appreciating the meaning of signs referring to numerical operations, understanding the underlying quantities and operations themselves, apart from the symbols that designate them. The ability to read and produce the signs of mathematics is more often a left hemisphere function, whereas the understanding of numerical relations and concepts seems to entail right hemisphere involvement. Elementary difficulties in language can impair the understanding of number terms, even as impairments in spatial orientation can render inoperative the ability to use paper and pencil to carry out sums or geometrical demonstrations. Deficits in planning, secondary to frontal lobe lesions, prove crippling in dealing with problems that have many steps. Despite this variety, there is a fragile consensus that a certain area of the brain, the left parietal lobes, and the temporal and occipital association areas contiguous to them, may assume a particular importance in matters of logic and math. It is from lesions in this area of the angular gyrus that one gets the original adult version of the Gerstmann syndrome, a condition in which calculation, drawing, left-right orientation, and finger knowledge are supposed to break down in relative isolation of other cognitive faculties. A. R. Luria adds that lesions in this area may also reduce the ability to orient oneself in space and to understand certain grammatical structures, such as prepositional phrases and passive constructions. I deliberately employ the phrase fragile consensus. In my own view, firm evidence has yet to be established that this area of the brain plays the crucial role in logical mathematical thought. Regions in the parietal area may be important in many individuals, but an equally persuasive case can be made that in other individuals or with respect to other operations, structures in the frontal lobes or elsewhere in the right hemisphere can compromise key logical mathematical functions. I wish to propose a different account of the neurological organization underlying logical mathematical operations. In my view, certain neural centers may well be important for specific logical mathematical operations, such as the ones I have cited. But these centers do not seem as indispensable for logic and mathematical thought as certain areas in the temporal and the frontal lobes appear to be in language or music. There is, in other words, considerably more flexibility in the human brain, in the way that such operations and logical implications can be carried out. A solution lies, I think, in the work of Piaget. The ability to carry out logical mathematical operations commences in the most general actions of infancy, develops gradually over the first decade or two of life, and involves a number of neural centers that work in concert. Despite focal damage, it is usually the case that these operations can nonetheless be carried out. Because the operations inhere not in a given center, but in a generalized and highly redundant form of neural organization, logical mathematical abilities become fragile not principally from focal brain disease, but rather as a result of more general deteriorating diseases, such as the dementias, where large portions of the nervous system decompose more or less rapidly. I think that the operations studied by Piaget do not exhibit the same degree of neural localization as those that we have examined in other chapters, and that they therefore prove relatively more fragile in the case of general breakdowns of the nervous system. In fact, two recent electrophysiological studies document considerable involvement of both hemispheres during the solution of mathematical problems. As one author puts it, each task produces a complex, rapidly changing pattern of electrical activity in many areas in front and back of both sides of the brain. In contrast, abilities like language and music remain relatively robust in the case of general breakdowns, provided that certain focal areas have not themselves been especially singled out for destruction. In sum, there is a rationale to the neural organization of logical mathematical abilities, but it is a far more general kind of representation than we have hitherto encountered. Wielding Occam's razor, one could conclude that logical mathematical ability is not as pure or autonomous a system as others reviewed here, and perhaps should count not as a single intelligence, but as some kind of supra or more general intelligence. I have at times felt sympathy for this argument and do not want in these pages to come off as more definitive than I actually feel. However, in my view, the fact that one can encounter specific and particular breakdowns of logical mathematical ability, as well as many kinds of extreme precocity, makes the elimination of logical mathematical intellect far too extreme a scientific maneuver. After all, most of the signs of an autonomous intelligence register positively in the case of logical mathematical thought. Moreover, it is also possible that logical mathematical competence may simply involve the concatenation of a number of essential but somewhat redundant systems. Were these to be destroyed discretely and simultaneously, an event that could come about only through impermissible experimental intervention, one would then encounter syndromes focused to the same degree as those in the linguistic and musical realms. That the concerns of this chapter are not parochial to the West is amply documented by the many systems of number and calculation that have evolved in different corners of the world. From the counting in terms of body parts found among Papuan New Guineans to the use of cowrie shells for market transactions in Africa, we see ample evidence of the agility of the human mind in wedding our natural proclivities to order and count to the carrying out of functions considered important in diverse cultural settings. Throughout the history of Western anthropology, there has been a running debate between those scholars who discern an essential continuity between Western and other forms of thought, and those who emphasize the primitiveness or savagery of the non-Western mind. This controversy shows no signs of abating soon, though claims that the mind of the savage is radically different from our own are not made nearly so readily these days as they were some decades ago. Because mathematics and science are among the proudest achievements of Western society, it is not surprising that the initial claims for superiority came in these areas. Considerable energy was invested in determining whether primitive individuals do or do not have the same logics that we have, can or cannot calculate accurately, have or lack a system of explanation that allows experimentation and disproof, and other such conundrums. In general, when Western social scientists imported their methods of testing and searched in alien lands for their own modes of thinking, they found little evidence for them, and so, for example, initial transportation of Piagetian tasks to exotic societies revealed that few individuals scored beyond concrete operations. Sometimes even the ability to appreciate conservation failed to be exhibited. Conversely, when evidence was accrued about thinking within the culture itself, particularly in tasks that mattered to the inhabitants, alleged differences between primitive and domesticated minds were lessened, and indeed, sometimes the primitives came off as superior to the investigators. One way to enter into this controversy, without being overwhelmed by it, is to think of non-Western societies in terms of the various scholarly roles I have described. When one searches in other traditional cultures for explicit evidence of the mathematician or the scientist, as we know him, there emerges little evidence that such concerns matter. A desire to build up an elaborate, abstract system of mathematical relations for its own sake, or to come up with experiments to test a set of propositions about how the world works, does seem to be a concern of the Western world. Commencing in Greek times, but really launched with a vengeance in the Renaissance, and now spreading rapidly to every corner of the globe. Analogously, the accumulation of vast written records and debates on these topics seems a Western invention of the past few centuries. When one shifts the focus, however, and seeks the basic operations of mind on which sciences are based, one finds little reason to doubt the basic universality of logical mathematical thought. To be specific, where there is a market economy, individuals are perfectly capable of bargaining in their own self-interest, in removing items from sale when they will not fetch a good price, and in making trades that are equitable or advantageous. Where it is important to be able to classify objects, be it for botanical or for social reasons, Individuals are capable of coming up with elaborate and hierarchically organized systems and of utilizing them appropriately. Where it is desirable to have a calendar that allows one to perform actions on a regular basis, or a mode of calculation that is rapid and reliable, e.g., the abacus, societies have contrived solutions that are at least as adequate as ours. And while their scientific theories are not propounded in the patois of the West, Bushmen of the Kalahari use the same kinds of methods to make needed discoveries. For example, in hunting, they differentiate among those times when they have seen prey with their own eyes, when they have seen the tracks but not the animals themselves, when they have heard of the animals from others, or when one must remain uncertain because one has neither seen them oneself nor talked directly to individuals who have seen them. As Nicholas Blurton-Jones and Melvin Connor conclude in their study of Bushman hunting, the resulting body of knowledge was detailed, wide-ranging, and accurate. The processes of tracking, specifically, involve patterns of inference, hypothesis testing, and discovery that tax the best inferential and analytical capacities of the human mind, determining from tracks the movements of animals, their timing, whether they are wounded, and if so, how, and predicting how far they will go and in which direction, and how fast all involved repeated activation of hypotheses, trying them out against new data, integrating them with previous known facts about animal movements, rejecting the ones that do not stand up, and finally getting a reasonable fit. To suggest the ways in which logical mathematical intelligence has been enculturated, it may be useful to characterize some of the arithmetical systems of pre-literate groups. In many societies, individuals are able to come up with a reasonable estimate of the number of objects, individuals, or organisms in a field. In fact, estimation ability may be astonishingly powerful. Gay and Cole found that Capelli adults in Liberia succeeded much better than American adults at estimating the number of stones in piles ranging from 10 to 100 stones. In comparison with the algorithms used in the West, systems based on estimating have the advantage that an individual will almost never be wildly off in a calculation. Using our algorithms for calculation, we are more likely to be completely accurate, but also far more likely to come up with a total that is widely off. If, for example, we misalign the columns in a sum or press the wrong buttons on a handheld calculator. If, in fact, one is looking for instances of highly developed numerical ability in Africa, the best place to look is in a game such as Kala, also called Malong or Owar Ray, a pit and pebbles game considered the most arithmetical game with a mass following anywhere in the world. The basic idea of this intricate game is to drop seed seriatim in holes around a board and to capture one's opponent's seeds by placing the final seed in one's hand in an opponent's hole that harbors one or two seeds. Observing individuals at play in this game, Cole and his colleagues found that winners used clear and consistent sets of strategies. The winning player makes sure he has solid defenses, that he catalogs the possibilities of every move, that he reserves time to himself, that he lures the opponent into making premature captures, that he moves for decisive rather than piecemeal victories, and that he is flexible in redistributing his forces in preparation for new assaults. Inasmuch as games can last 300 or more moves, the skilled Pele player must wield these strategies with considerable finesse. And indeed, excellent players bring honor to their family and may even be commemorated in song. Some uses of numerical abilities are straightforward, as for example in trade or in keeping track of possessions. One also finds, however, mathematical thinking intertwined with religious and mystical pursuits. Among the Jewish people, insights into numerical properties were closely tied to interpretation and, at times, to prophecy. In the Spanish Inquisition, one could receive life imprisonment or even a death sentence if one possessed Arab manuscripts dealing with mathematics. Mathematicians were denounced as the greatest of all heretics. Medieval Islamic and Christian scholars believed that magic squares, arrays in which all the rows and columns sum to the same total, could ward off the plague or cure sterility. And in many parts of Africa, there is a taboo on counting humans, domestic animals, or valuable possessions. The interrelation between numerical and other symbol systems has also been central to activities of various sects. Medieval Indians substituted evocative words for numbers, moon for one, eyes or arms for two, and wrote their mathematical and astronomical treatises in verse. Even today, the manipulation of elaborate systems in which words and numbers stand for one another, and secret messages can be conveyed through strings of numbers, is a skill cultivated by Islamic scholars. When it comes to a sensitivity to numerical properties, then, both pre-literate and traditional literate societies recognize these skills as being important. The numerical core of mathematical intelligence seems to be honored universally. Still, a seemingly strong challenge to the rationality of the primitive mind is the evident embracing by individuals of positions that logically are inconsistent with one another, positions that invoke the supernatural as well as the occult. How can individuals who would propose to be rational believe that they can be a cat at the same time as a human? That childbirth is due to the movement of the stars and the like? Earlier commentators might have been tempted to pounce on or attempt to deny this apparent irrationality, but some anthropologists now make a different analytic move. In their view, all peoples, not excluding those in our society, hold on to many beliefs that are non-rational, if not simply irrational. Indeed, it is impossible to exist as a thinking human being without subscribing to many beliefs, at least some of which will turn out to be inconsistent with one another. One need think only of the beliefs of our religions, and even the beliefs of science are often inconsistent with one another. Consider, for example, the belief in scientific themata without any logical reason for them, or the belief on the part of physicists in predictability as well as in indeterminacy. What is important to note here is that, however strongly they may be held, these beliefs do not actually interfere with how one makes decisions on a practical day-to-day basis. In fact, if these beliefs do so interfere, one is seen as crazy, irrespective of the society in which one happens to live. Instead, they are seen as cosmological or metaphysical theories that have to do with the ultimate nature of reality, and not with how one grills a piece of meat, gets from one place to another, or strikes a deal with an acquaintance. It is in these everyday sites of reasoning, and not in our cosmologies, be they mythological or scientific, that the daily practices of human beings are carried out. Even as numerical thinking is readily found across traditional cultures, high levels of logical thinking can also be discerned. In an elegant study of land tenure disputes in the Trobriand Islands, Edwin Hutchins has demonstrated that litigants in a dispute are capable of long and complex chains of reasoning. According to Hutchins' account, every litigant who wants to demonstrate his ownership of a garden must produce a culturally meaningful account of the history of the garden that terminates in the state where the litigant himself has rights to own the garden. He also is well advised to show that there exists no reasonable history of the garden that terminates in his opponents having a plausible claim to that garden. In some respects, notes Hutchins, the problem-solving task of the litigant is akin to theorem proving in mathematics of logic. The cultural code provides the axioms or implicit premises of the system. The historical background of the case, and especially the state in the past at which the litigants agree on the disposition of the garden, provides the explicit premises of the problem. The theorem to be proved is a proposition which represents the litigant's own rights in the land. In Hutchins's judgment, the model of folk logic that has been developed from purely Western sources proves adequate as an account of the spontaneous chains of reasoning displayed by the Trobriand litigants. To be sure, it is not straight Aristotelian logic, because it contains plausible as well as necessary inferences. But, as Hutchins points out, so does our own reasoning. But if, as a result of such studies, the differences in rationality between us and them have been minimized, there is also a fresh recognition that schooling in general, and literacy in particular, can bring about major changes in the ways in which individuals think about themselves, and in how they communicate with other people. As I shall discuss in detail in Chapter 13, one learns in school to deal with information outside of the context in which it is generally encountered, to entertain abstract positions and to explore the relations among them on a hypothetical basis, to make sense of a set of ideas, independent of who says them or of the tone of voice in which they are said, to criticize, to detect contradictions, and to try to resolve them. One also acquires a respect for the accumulation of knowledge, for ways to test statements in which one does not have an immediate interest, and for the relationship between bodies of knowledge that might otherwise seem remote from one another. This valuing of abstract concerns which relate to reality only by a lengthy chain of inference and a growing familiarity with objective writing, reading, and testing, eventually spawns a person at home with the principles of science and mathematics and concerned about the extent to which his views and behavior accord with these somewhat esoteric standards. In many primitive societies, there is little encouragement to ask questions, to challenge the established wisdom, to question magical or mystical explanations. In contrast, the whole thrust in many schooled environments is to challenge statements made without evidence, to attempt to reformulate faulty arguments, and even to forge new syntheses on one's own. The end result is a society that cares deeply about the logical, scientific, and mathematical concerns that I have reviewed here, even, it would appear, at the expense of some of the more aesthetic or personal forms of intelligence that I have reviewed elsewhere in this volume. In treating the effects of schooling and literacy on the attitudes of a population, I touch on an important aspect of logical mathematical thought that I have so far minimized. While scientists and mathematicians like to think of themselves as concerned with the eternal verities, their pursuits are in fact rapidly developing and have already undergone profound changes. Conceptions of these realms have also changed over the centuries. As Brian Rotman points out, for the Babylonians, mathematics was a way of astronomical reckonings. For the Pythagorean, it was thought of as an embodiment of the universe's harmonies. For scientists of the Renaissance, it became a means of uncovering nature's secrets. For Kant, it was the perfect science whose propositions were constructed in the deepest layer of our rational faculties. While for Frege and Russell, it became the paradigm of clarity against which ambiguities of ordinary language could be judged. These views will no doubt continue to change. In fact, among leading mathematicians, there are profound differences of opinion about the nature of their whole enterprise. Which goals are paramount? Which methods of discovery are allowable and which are not? Science, of course, changes as well. The change is often seen as progress. But after the provocative writings of Thomas Kuhn, commentators are more hesitant to see science as marching in a unilinear path toward final truth. Few would go so far as some Kuhnians have gone and declare that science is simply the substitute of one worldview for another, or to deny, with Paul Feyerabend, the distinction between science and non-science. But there is considerable recognition that each worldview clarifies certain issues while neglecting or obscuring others, and that the goal of a single science, one unified across all fields, is a chimera that one would do well to exercise. As one investigates particular scientific work, it is important to know who is writing against what and who is writing for what end. True, within the execution of normal science, where the basic paradigm can be assumed, there may be less reason to vex over the roots of one's work. And there may be steady progress toward defining the answers to problems within a circumscribed field. But once one has come to recognize that a scientific consensus may be overthrown tomorrow, the changing nature of science becomes simply a fact of life. Individuals are beneficiaries but also victims of these time changes. A person with one set of skills may be a tremendous mathematician or scientist in one era, because his skills are just what was needed, while proving relatively useless in succeeding or prior historical epochs. For instance, the ability to recall vast strings of numbers or to envision complex relations among forms may prove tremendously important in certain mathematical eras, while of little use at other times, where books or computers have taken over such mnemonic functions, or where the notion of spatial concepts as integral to mathematics has not been accepted. This accident of timing was conveyed most poignantly in the case of the Indian Srinivasa Ramanujan, generally considered to be one of the most talented natural mathematicians of recent centuries. Unfortunately, Ramanujan came from a rural site where there was no knowledge of modern mathematics. On his own, he had contrived many years of mathematics, well in advance of mathematics as it was then practiced in his own home. Ramanujan finally moved to England, but it was too late for him to contribute to the field as it was practiced in the present century. G.H. Hardy found it fascinating to teach the mathematics of today to someone who had the deepest instincts and insights but had literally never heard of most of the questions being addressed. As he lay dying, Ramanujan told his teacher, Hardy, who had just arrived in a taxicab, that the number 1729, the number of the cab, was not, as Hardy had supposed, a dull one, but rather the smallest number, that could be expressed as the sum of two cubes in two different ways. This was an absolutely amazingly rapid mathematical insight, but not the sort of contribution that was at a premium, or even especially appreciated, in the mathematical circles of 20th century Britain. Beyond natural gifts, aspiring mathematicians must be in the right place at the proper time. Mathematics and science may accumulate and change, but are there not in these areas at least some fundamental laws that remain immutable? The renowned American philosopher W. V. Quine has written convincingly on this issue. As he points out, we change our conceptions of history and economics more readily than those of physics, and those more willingly than laws of math and logic. Mathematics and logic, central as they are to the conceptual scheme, tend to be accorded such immunity in view of our conservative preference for revision which disturbs the system least. And herein, perhaps, lies the necessity which the laws of mathematics are felt to enjoy. And yet Quine indicates in each area, including logic and math, there is a constant drift and drive toward simplicity. Accordingly, mathematics and logic themselves will be revised whenever essential simplification of the whole conceptual enterprise of science is likely to result. If our century is any indicator, change will become ever more rapid. There has been as much science in the past few decades as in all human history before. Moreover, the proliferation of new fields and of hybrid fields and the explosion of new technology, most prominently the computer, make it difficult even to envision the scope of the scientific enterprise in the future or the issues to which logical and mathematical talent may be applied. Certainly, scientists will make even greater use of new technological innovations, and it is a rash person indeed who would doubt that. Before long, computers will themselves be contributing to the process, not only by solving problems that would be beyond human energies to tackle by hand, but also by helping to define what the new problems will be and how they ought to be approached. Forms of life created by genetic engineering and new robots with person-like qualities may complicate the picture even further. And perhaps more so than in the past, individuals ignorant of these advances and of their implications will be in an unfavorable position to participate productively in the society. The drift of our own society, and perhaps of other societies as well, raises sharply the question whether logical mathematical intelligence may not be in some way more basic than the other intelligences. More basic, in a conceptual sense, as lying at the center of all human intellect, or more basic in a practical sense as guiding the course of human history, its concerns, its problems, its possibilities, and, perhaps, its ultimate constructive or destructive fate. It is often said there is, after all, only one logic, and only those with developed logical mathematical intelligences can exercise it. I do not agree. It should be apparent from this chapter that logical mathematical intelligence has been of singular importance in the history of the West, and its importance shows no sign of diminishing. It has been less important elsewhere, and whether the present unifying trends will continue is by no means certain. To my way of thinking, it is far more plausible to think of logical mathematical skill as one among a set of intelligences, a skill powerfully equipped to handle certain kinds of problem, but one in no sense superior to or in danger of overwhelming the others. Indeed, there are even different logics with contrasting strengths and limitations. As we have seen in earlier chapters, there is indeed a logic to language and a logic to music. But these logics operate according to their own rules, and even the strongest dosage of mathematical logic into these areas will not change the ways in which their endogenous logics work. To be sure, there have been and will continue to be productive interactions between logical mathematical and spatial intelligences in areas like chess, engineering, and architecture, and some of these synergistic applications will be touched upon in the treatment of spatial knowledge in the next chapter. Beyond question, then, there can be various links between logical mathematical and the other forms of intelligence that I am examining here. And as science and mathematics continue to expand, there is every reason to think that even stronger and more extensive bonds will be established with other intellectual domains. But as the definition of these fields changes, one can also raise another question. Does it still make sense to group all of logic and mathematics together as one form of intelligence and to set it off sharply from other forms? Only time can tell whether the grouping that I have proposed here has long-term validity. At present, I remain persuaded that the line of development described by Piaget, which begins with an intuition of number and an appreciation of simple cause and effect, can be traced through to the highest reaches of contemporary logic, mathematics, and science. And what of the tie to music, with which the last chapter concluded? Can it simply be an accident that so many mathematicians and scientists are attracted to music? And what of the striking commonalities among the energizing ideas in areas like music, the visual arts, and mathematics, as conveyed by Douglas Hofstadter in his justifiably acclaimed Gödel, Escher, Bach? A clue to this conundrum comes from the fact that while mathematically talented individuals are often intrigued by the order or patterning found in apparently remote areas, ranging from G.H. Hardy's fascination with cricket to Herbert Simon's interest in architectural planning, these interests have not been necessarily reciprocated. It is possible to be a gifted sculptor, poet, or musician without having any particular interest in or knowledge about that orderliness and system that form the centerpiece of logical mathematical thinking. What we encounter in these apparent coincidences of fields are simply, but properly, instances of the intelligences of the logician, the scientist, or the mathematician, as they are applied to other domains of experience. There will, of course, be patterns or orders wherever one looks, some trivial, some not, and it is the special genius, or curse, of logicians and mathematicians to discern these patterns wherever they happen to be found. It may even be the case, as individuals from Plato to Leibniz thought, and as Einstein continued to hope, that these echoing patterns harbor something of the secret of the universe. But perceiving these patterns and making something of them is an example of the logical mathematical intelligence at work, working well or working badly, but displaying its own wares. It does not reflect the core operations of other forms of intelligence. It does not tell us what musical or linguistic or bodily intellect is centrally about. To see these other competences at work, we need to look at the kind of novel that a Saul Bellow might write, perhaps about a mathematician, or at the kind of ballet that a Martha Graham might choreograph, perhaps about a set of equations or a proof. Each intelligence has its own ordering mechanisms, and the way that an intelligence performs its ordering reflects its own principles and its own preferred media. Perhaps in Bali, one or another aesthetic faculty occupies the same apparent superordinate ordering privileges that we in the West are likely to attribute, almost reflexively, to the abilities exhibited by a mathematician or a logician. That's it for today. If you enjoyed this video, you might want to check our link in the description, where you'll find Gardner's book summary and many other fundamental persuasion books in different languages. And don't forget to subscribe to the channel for more psychologic and marketing content. See you in the next one.